Hello, 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 hello. Okay, so everything is good now. Okay, so we had done up to momentum of a photon in the previous class. Okay, now we are going to move on towards wave particle duality. Okay, we are going to move on towards wave particle duality. So put the heading wave particle duality. Let's write over here wave particle duality. Okay. So, wave particle duality implies that these are basically what? Matter waves. Okay. These are basically matter waves. Matter waves. Okay. So, matter waves, this is very kind of abstract kind of wave. We all know this very well. But this concept is so important that if you look at the PYQs from 1991 till 2021, if you have a look at the PYQs, then you will find that this single concept has been asked 21 times. Okay, the same question has been repeated 21 times in last 30 years. Okay, so how much high is the frequency of this topic, you can understand from this. And those of you who haven't watched the videos from the first class, they can go to the playlist, link is there in the description, they can watch from the first class. Okay, so no worries, you can watch from the first class. Only 3 lectures have been done so far. Okay, so don't worry about that. And special thanks to Karan Chaudhary. Okay, today's special person. Okay, Karan Chaudhary. So special thanks to him for giving him me the love. Okay, so I will write his name over here. Okay, Karan Chaudhary. So special thanks to this person. Okay, he liked my videos and he loved it actually. Okay, so wave particle duality, we will move on towards the main thing. Now it was given by D. Broglie. Okay, D. Broglie gave this hypothesis. Okay, D. Broglie hypothesis. Now we often say that it is D. Broglie, but its correct pronunciation is D. Broglie. Okay, it's D. Broglie. Okay, its correct pronunciation is D. Broglie. Louis D. Broglie. Okay, but for my convenience, in order to not give the pain to the throat, so I will only say De Broglie only, but its correct pronunciation is De Broglie. Okay. If in interview you have physics optional, right? So in interview, if they ask something about De Broglie hypothesis, then do not pronounce it as De Broglie in the interview. Okay. Only in the interview, pronounce it as De Broglie always. Okay. For my convenience, I am saying De Broglie in this video. Okay. So that's the thing. Okay, so D. Broglie, what he said, that moving particle is associated with wave or wave packet known as matter wave. Okay, he simply said that moving particle is associated with wave or wave packet known as matter wave. Okay, so uh, this wave is very different kind of wave beta. This wave is not the one which we can see. Okay, like mechanical wave. What are mechanical waves? You know this very well, that mechanical waves are like sound waves. Okay, mechanical waves. What are mechanical waves? Mechanical waves are like sound waves, water ripples, okay, sound waves, water ripples. What are these? These are basically mechanical waves which you can see with the eyes, okay. Even the sound waves you can feel the vibrations, okay. If you touch the microphone of your mobile right now, the speaker of your mobile right now, then you will feel the vibrations. So these are basically mechanical waves which can be felt or seen, okay. These can be either they can be felt or they can be seen, okay. These are such waves, these are mechanical waves. But what are these matter waves? Matter waves are not such waves. These are very abstract kind of waves, okay, very much abstract. What do you mean by abstract? Abstract means which cannot be visualized, very hard to visualize, okay, very difficult to visualize, okay. And these difficult to visualize wave do not mean that the wave the particle travels in this form. It does not mean, okay. Particle never travels in this form, okay. If you say that de Broglie hypothesis says that every particle has a wave associated with it, then the particle is traveling in the form of a wave. If you say such thing, then it is completely a blunder, because particle is not traveling in this form, okay. Neither is it traveling in the form of compression and rarefaction as in sound waves. In sound waves the particle travels in the form of compressions and rarefactions, okay. But here and in the case of water ripples, the water travels in the form of waves, and these waves move forward, okay. But these waves are very different. These are totally abstract kind of wave with an complex wave function, okay. Complex wave function they have. Complex wave function. Complex wave function means no one even knows that these waves ever do exist or not. No one knows in the world. No one knows this thing. No one in the world ever knows whether matter waves even exist in reality or not. Okay. This no one knows. Okay. If I take a microscopic particle, okay. If I take a microscopic particle, what are microscopic particles? Subatomic particles. Okay. If I take a microscopic particles such as electron, proton, neutron, deuteron, alpha particle, etc., then the thing is that in case of these microscopic particles, these matter waves are significant. Okay, these matter waves are very much significant. Okay, because I had told you in the first lecture that a ball having radius of 2 meter. Okay, a ball having radius of 2 meter was having an uncertainty in position how much? 10 to the power minus 32 order, of the order of 10 to the power minus 32 meter. The uncertainty in position of a 2 meter radius ball was 10 to the power minus 32 meter, whereas for an electron whose radius is 10 to the power minus 17 meter, the uncertainty in position came out to be 1 centimeter. Okay, so the electron of 10 to the power minus 17 meter radius can be found anywhere in this 1 centimeter range. Okay, but a 2 meter radius ball, if I say that it can be found anywhere in the 10 to the power minus 32 meter range, then it does not make sense, because this is completely negligible. Because if you draw the trajectory of a 2 meter ball, you will draw it like this. And if you say that 10 to the power minus 32 meter uncertainty means the ball can move 10 to the power minus 32 above or below this trajectory. Okay, this definite trajectory has an uncertainty of 10 to the power minus 32 meter. So I can say that the 2 meter radius ball can be found anywhere between these, and these are what, 10 to the power minus 32 meter above and 10 to the power minus 32 meter below. So this 10 to the power minus 32 meter is completely negligible. It is not even, it is such a small quantity that you can't even imagine. Even the electron's radius is far much greater than this. Okay. So such a small uncertainty can be totally neglected, and you can clearly draw the trajectory of a macroscopic ball. Okay, you can clearly draw the trajectory. But for an electron, if you try to draw such a trajectory, then electron's radius is only 10 to the power minus 17 meters. So electron will look like a point, and 1 centimeter uncertainty in its position. I have already discussed this in the first lecture. So 1 centimeter uncertainty in its position, it means that the electron can be found anywhere like this. 1 centimeter will be so huge for such a small electron that the electron can be uncertainty in position from this trajectory. The electron can go 10 to the power, 1 centimeter above and 1 centimeter below this trajectory. So for this electron, this uncertainty is very large. Okay, so we cannot ignore this 1 centimeter. And in case of 2 meter radius ball, the uncertainty was 10 to the power minus 32 meter. So the trajectory can be drawn sharply. But over here, the trajectory can't be drawn sharply because 1 centimeter distance above and below it is going, right? Yes. So such is the concept with this also. Okay, if you calculate the de Broglie wavelength of a macroscopic object, then it is going to be very much negligible. Okay, and this matter wave is associated with every particle. It simply means that that the there may be some kind of what we can say wave function associated with it. There may be some kind of wave function associated with it, and that wave function may be in the form of this. We can represent it like this, and such in such form the particle, actually the particle does not travel like this, but for pictorial representation we show the particle like this, that the particle can be found anywhere within this wave. Okay, this is a single wave packet I am assuming, and the wave of a matter wave means what, wave packets of particles. Okay, so wave packets of particles are like this, and this matter travels in the form of this. But for macroscopic world, this wave comes out to be so short that it can be completely neglected as compared to the size of the particle. Okay, so de Broglie simply said that de Broglie wavelength he gave. Okay, he gave de Broglie wavelength, and this de Broglie wavelength was given as momentum of a photon. Okay, momentum of a photon is given like this. Okay, this is the formula of momentum of photon, right? We had learnt in the previous class. Momentum of a photon. Okay, now lambda comes out to be h by p. Okay, so what de Broglie said is that the formula which you are applying for a photon, okay, this is the formula for wavelength of a photon. De Broglie simply said that whatever formula you are applying for photon wavelength, you can simply apply the same formula for a matter, and if you apply the same formula for a matter, then you will get the matter wavelength. Okay, matter waves wavelength. Okay, matter waves wavelength you will get through this formula. Okay, so simply the formula was like this, and matter waves wavelength you will get through this formula if you put the momentum of particle over here instead of momentum of photon. Okay, so you will get de Broglie wavelength. Okay, so the difference is nothing between a photon and a wave, a particle. A photon is just a massless particle, and it is traveling in the form of wave packets, and a particle like electron is also traveling in the form of wave packet, but the wavelength wave associated with an electron like particle which is solid, it is actually matter wave, because electron is a matter, proton is a matter, so it is a matter wave. But the wavelength associated with photon, if you put the value of p, momentum of a photon over here, then you will get wavelength of the light actually. Okay, so whatever formula we can use for the wavelength of the light, the same formula can be used for the wavelength of a particle. Okay, this is what de Broglie suggested. Okay, so then, according to de Broglie hypothesis, this is the equation. This is our equation, right? Which is for the matter wave, and this matter wave is of very abstract nature. Okay, it can't be imagined so means easily. Okay, not imaginable so easily. It is very much abstract kind of wave. Okay, so according to de Broglie equation one, above equation can be used. ठीक है ना? This is the equation for photon. Okay, this was the equation for photon given by Planck, I think. Yes, Planck gave this equation. Okay, but according to de Broglie, above equation can be used. Above equation can be used for material particle without modification. Okay, okay, so the above formula can be used for material particle without any modification. So simply P will be equal to mv. Okay, according to Newtonian formula. So we will put P equal to mv over here. This is for non-relativistic motion. Okay, P equal to mv is for non-relativistic motion. So if the particle is performing a non-relativistic motion, then clearly you can put lambda equal to h by mv, you will get. Okay, and after that, you know this very well, that mass is given by the relativistic variation like this. Okay, special theory of relativity tells like this, that mass is given for like this, for a particle traveling with velocity v, mass is given by this formula. Okay, where m naught is the rest mass of the particle. Okay, m naught is the rest mass of the particle, rest mass of particle. Okay, so m naught is the rest mass of the particle and v is the velocity of the particle over here. Okay, velocity of particle. Okay, okay, so it is velocity of the particle. V by c you can put as beta. Okay, v by c you can put as beta. Okay, so you can write this as, you can write this like this, m equal to m naught divided by 1 minus v square by c square power half. Okay, equal to m naught. Okay, 1 minus beta square power half. Okay, and then you this term in itself is gamma. Okay, you know this very well. In the special relativity, this term is called as gamma. Okay, this whole term, this term gamma is equal to basically this. Okay, 1 upon 1 minus v square over c square to the power half. Okay, this is what is gamma. Okay, so if we consider the relativistic motion, then lambda equal to h by mv will be replaced by, this m will be replaced by gamma m naught. Okay, why gamma m naught? You can clearly see over here. M will be replaced by gamma m naught. Okay, for a relativistic particle. So you will put over here that h upon gamma m naught into v. Okay, right? So if the motion is non-relativistic, then what will happen? You only tell me. Okay, if the motion is non-relativistic, suppose if the motion is non-relativistic, If the motion is non-relativistic, then you can clearly state that v is much smaller than c, and as v will be much smaller than c, then the term over here, that v by c, will almost tend to 0. Okay, almost equal to 0. So v by c will be almost equal to 0 over here, and v by c, as it will be almost equal to 0 over here, so m will come out to be equal to m naught for smaller velocity. Okay, for small v. Okay, so for smaller velocities, m will come out to be equal to m naught. Okay, clearly. So m will be equal to m naught for smaller velocities. So lambda will come out to be, you can write this, if the motion is non-relativistic, you can write, ठीक है ना, kinetic energy of the particle. Okay, if motion is not relativistic, then kinetic energy of a particle is given like this. Okay, kinetic energy for non-relativistic motion. Okay, kinetic energy for non-relativistic motion, and you know this very well, that p equal to half mv square. Okay, half mv square. If you put this value over here, not p, sorry, p is not equal to half mv square. Okay, p equal to mv. Okay, so p equal to mv, if you put over here, so p equal to mv, if you put over here, then what will happen? M square v square divided by 2m. Okay, m square v square divided by 2m is going to come, and this 1 m will cancel out from here, and ultimately you will get half mv square. Okay, so that's why the formula has come like this. The relation between kinetic energy and momentum, this is basically classical. Okay, classical, or you can say non-relativistic. Okay, non-relativistic. Why non-relativistic? Because there is no variation in a moving particle's mass. Okay, in the theory of relativity, you have learned that moving particle has some change in the mass. Okay, if a particle has some velocity, there is a variation in its mass. Okay, but over here, our particle is such that its velocity is very small, and is as its velocity is very small, so Newtonian mechanics can be applied, and as Newtonian mechanics can be applied, so it is quite obvious that you can take the moving mass as rest mass itself. Okay, because if you put v is very smaller than c over here in this formula, then you will get v by c equal to 0, and this will be m equal to m naught simply. Okay, so in this way you will get this. Okay, so this is the formula for E, and so from here P comes out to be equal to square root of 2me. Okay, 2m into kinetic energy square root is equal to momentum of the photon. Okay, not photon, momentum of the particle. Okay, momentum of the particle equal to square root of 2me is going to come, and after that you know this very well, that you had found out that h upon p, lambda equal to h upon p, by de Broglie hypothesis. So for non-relativistic motion, but from de Broglie hypothesis, you had known this very well. Okay, from de Broglie hypothesis, you know this very well, that lambda equal to h by p, and p's value is square root of 2me. So p's value, if you put over here, then lambda will come out to be h upon square root of 2me. Okay, okay, so lambda's value is going to come out to be like this for classical. Okay, classical concept. Okay, for classical concept, classical concept means smaller velocities as compared to velocity of light, smaller velocities. Okay, for smaller velocities, this is going to be the concept. Okay, and all these derivations have been asked in the UPSC physics optional PYQ. If you see, then these equations have been asked to derive simply. Okay, so all these things you will have to remember. Okay, you have to cram all these things in your head. Okay, so this is the thing. Now de Broglie wavelength of gaseous molecule. Okay, now we will move on towards our next concept, which is de Broglie wavelength for a gaseous molecule. Okay, de Broglie wavelength De Broglie wavelength of a gaseous molecule. Okay, we are going to learn this now. Okay. Yes, so hopefully now everything is good. So de Broglie wavelength of a gaseous molecule, if we want to find out, then what will it be? Okay. So for a gaseous molecule, gas in thermal, all these things are going to come in paper 1. Okay. All these things are going to come in paper 1 in the kinetic theory of gases. Okay. So I won't go into the details of it. Okay. Gas in thermal equilibrium. Okay. You simply note down these facts. Okay. Thermal equilibrium at temperature T. Okay. Velocity or energy distribution is Maxwellian. Okay. So gas is in thermal equilibrium and temperature T, velocity or energy distribution is Maxwellian. When this is given in the question, when these two things are given in the question, okay, then you have to simply use this formula. Just remember it for the time being. When we will cover paper 1, you will eventually get the clarity. Okay, I can't explain it right now because the we will digress from the topic unnecessarily. If I discuss KTG over here, then we will digress from the topic, main topic. Okay, so average translational kinetic energy per molecule, E equal to 3 by 2 kT. Okay, K is Boltzmann constant. Okay. Okay. So you will eventually put the value lambda equal to, what is the value of lambda? H upon square root of 2 me. You had proved earlier. So you will put this value over here. Okay. T is the temperature and basically K is Boltzmann constant. Okay. So you will put this value over here. Then you will get what you will get, 3 square root of 3 m kt. Okay. Okay, this is the thing which you will get. You will put this over here. Basically, what is there in it? Okay, 2m into 3 by 2 kt, then 2 will 2 cancel out, 3m kt. Okay, so this formula is for the gas in thermal equilibrium at temperature T, and when the velocity and energy distribution is Maxwellian, then this formula is applicable. Okay. Now this is also valid. Write a note over here that this is also valid for a system of neutrons in thermal equilibrium. Okay, so this is also valid for a system of neutrons in thermal equilibrium. Okay, so now the second formula comes for thermal neutrons. Okay, for thermal neutrons. What are these thermal neutrons? It will be covered in KTG, okay, kinetic theory of gases, but it is not there in this portion. Paper 2 का part नहीं है वो, paper 1 का part है, okay, it is a part of paper 1, okay. So 0.025 electron volt less than 0.025 electron volt. The energy when it is less than 0.025 electron volt. If suppose there is a neutron whose energy is less than 0.025 electron volt, then it is called as thermal neutron. And for such thermal neutrons, E equal to kT. Okay, and okay, so it is like a linear harmonic oscillator. Okay, it is similar to a like a linear harmonic oscillator. Okay, so E equal to kT, and eventually you will get lambda equal to what? Lambda equal to, you will get what? You will get lambda equal to h by square root of 2 mkt for thermal neutrons. Okay, this is for thermal neutrons. For thermal neutrons you will get h divided by 3m square root of 2 mkt. Okay, so this is the formula for thermal neutron, and you have to by heart these formulas. Okay, direct numerical is asked based on these formulas, all these formulas. Okay, direct numerical is asked. If a charged particle of charge q, again it is just a fact. Okay, if a charged particle of charge q okay, let me write over here. If a charged particle of charge q, okay, charge q is accelerated by an accelerating potential v such that it acquires non-relativistic motion, that is v is much smaller than c, then E equal to qv. Okay, and lambda will come out to be what? H divided by square root of 2me is the formula, right? Square root of 2me is the formula. So in the place of E you will put qv. So 2mqv you will get. Okay, so this is the formula for de Broglie wavelength, and all these basically as you will cover paper 1 na, all these things will become clear. If I discuss these over here na, then it will be completely digress from the, we will completely digress from the topic itself. Okay, so that's why just mug up these things. Okay, for the time being, that accept them as it is. Okay, accept this slide as it is, accept this slide as it is, accept this slide as it is. Okay, for the time being. Okay, so that we can later on cover the things. Okay, later on as I will cover the paper 1, then these things will be automatically get cleared. Okay, automatically they will be clear. Okay, but you keep making the notes. Okay, now from this formula, lambda equal to h divided by square root of 2 mqv. From this formula we can clearly write this formula for different things. Okay, for electron we can write. Okay, so for electron, what is the formula? You will put m equal to 9.1 into 10 to the power minus 31 kg. Okay, then you will put q equal to e equal to what? 1.6 into 10 to the power minus 19 coulomb. Okay, you will put this. So as you will put these values over here in this formula, so you will get lambda to be equal to 12.27 divided by square root of v multiplied by 10 to the power minus 10 meter you will get. Then you will convert this into angstrom. So when you will convert this into angstrom, you will get basically 12.27 divided by square root of v angstrom. Okay, because 1 angstrom is equal to what? 10 to the power minus 10 meter. Okay, all these formulas you have to learn by heart, because these are going to basically uh, uh, problems have been asked based on these. Okay, so now for a proton, what will be the value? So for a proton, this, just by heart this. Okay, for a proton, I don't remember the mass of a photon, proton, not photon, proton. I don't remember the mass, but I think there should be something else. Okay, uh, so okay, this is the formula for a proton. When you will put value of m q over here for a proton, then and a value of h, obviously h value also you will put. Okay, so h is equal to 6.63 into 10 to the power minus 34. You know that already. Okay, so for a proton, this is the value. For a deuteron, for a deuteron, for a deuteron, deuteron is like this. Okay, plus electron. So this is basically your deuteron. Okay, neutron. Okay, so how is a neutron? First of all, you will take deuterium. Okay, what is, let me explain what is neutron. Okay, what is deuterium? What is neutron? Let me explain. Okay, uh, uh it is suppose you take this. So hydrogen exists in three isotopic forms. Okay, this is hydrogen. Okay, this is deuterium, and this is tritium. Okay, now you tell me one thing, that how much now let us draw the structures of this. So for a 1h1 means normal hydrogen, there will be one proton over here. Okay, and one electron over here. Okay, if we talk about the Rutherford model, then Rutherford model says that one electron is revolving around the proton. Okay, so but this is not correct actually. We cannot say that the electron is revolving around the proton. It is wrong to say like that. Okay, but for the time being, if you assume the elementary thing, then you can draw these structures. Okay, actually electron does not revolve. Electrons actually exist in the form of clouds. Okay, electron do not revolve, they exist in the form of cloud, because trajectory of a electron cannot be defined. I had already told you. Okay, trajectory of an electron cannot be defined. I had already told you in the first lecture. Okay, so it is wrong to say that electron is following a circular path. Okay, but Rutherford gave that model according to classical concept. Okay, which is he compared the planet electron atom model. He compared the atom model to the solar system like macroscopic world. Okay, what did Rutherford do? he basically compared the microscopic world with the macroscopic world, like the Earth and the Sun system, Moon and the Earth system, like that he compared. Okay, so it is called as basically planetary model, but it is completely wrong. We got to know later on. Okay, after later on we got to know that. Okay, so it is basically a classical concept. So according to Rutherford, I am drawing this diagram. According to Rutherford, I am drawing this diagram in order to understand neutron. Okay, so hydrogen will be like this, deuterium will be like this. Okay, one electron outside, and in the nucleus one proton and one neutron will be there, because the mass number is 2. Mass number is 2, so one proton and one neutron in the nucleus. Okay, one electron in the outside. Okay, and what will be the structure of tritium? Tritium will be basically one proton, two neutron, because the mass number is 3, right? So 2 plus 1 is 3. It cannot be more than one proton, because the atomic number will change if the number of proton will change, but the atomic number cannot change for the isotopes, because all the isotopes have the same atomic number. Only thing is they have different mass numbers. Okay, so in order to have different mass numbers, they should have different number of neutron. Okay, in order to have different mass number, they should have different number of neutron. Okay, so in order to achieve different number of neutron, I am drawing here in the hydrogen. This is hydrogen, so it has basically one proton in the nucleus and one electron is revolving according to Rutherford model. Okay, it is wrong to say that it is revolving, but if we consider the Rutherford model, then we can understand it like this. Okay, so hydrogen has one electron in the outermost shell and one proton in its nucleus. One proton in the nucleus, one neutron for deuterium. Okay, this is deuterium. Okay, so for deuterium, one proton, one neutron in the nucleus and one electron outside. And for a tritium, one proton and two neutron in the nucleus and one electron in the outer shell. Okay, so one electron. Now you only tell me you want to define neutron. Okay, so neutron is such a particle that if you remove one electron from here, okay, if you give ionization energy, if you provide it with ionization energy and remove this electron from here, so what will it become? It will become a positively charged ion. Okay, and as soon as it becomes positively charged ion, it will not be called deuterium, it will be called as neutron then. Okay, it will be called as neutron then, not deuterium. Okay, so neutron is H12 positive. Okay, so this is neutron. Okay, so this is neutron. So neutron, for a neutron, lambda will be equal to all these formulas you have to mug up literally. Okay, so that you can directly use these formulas in the numerical in the exam, because in the exam you don't have sufficient time to derive these formulas. Okay, in the IIT JEE exam, what happens is that you don't have to write subjective paper. So in the IIT JEE exam or CSR net exam, if you don't remember the result now, you can directly use the derive the formula then and there. Okay, in the CSR net exam or any objective exam for that matter, you can derive the formula then and there, but this is a subjective exam, you will fall short of time over here. So you have to literally mug up these formulas and use these directly in your numerical problem. Whenever the problem comes on proton, then directly you have to use this formula. Whenever the problem directly comes on neutron, you have to directly use this formula, and so on and so forth. Okay, so you have to literally mug up these formulas so that you don't fall short of time in the exam. Okay, and if you derive the problem formula there na, you will really you can't complete the paper in time. Okay, because the paper is very lengthy. Okay, so for an alpha particle, now what is the case with an alpha particle? Now let me explain an alpha particle. What is it? Okay, so you all know that helium 24. Okay, it is represented like this. But do you know, according to Rutherford model, two protons and two neutrons will make up a helium nucleus, and two electrons will revolve finally. around this. Okay, according to Rutherford model, then 2 electrons will revolve around this. Okay, so in order to achieve an alpha particle, I will provide first ionization energy number 1, okay, and remove this electron. Then I will provide ionization energy number 2. Then I will remove this electron. Okay, and when both these electrons are removed, then you are left with nucleus consisting of 2 proton and 2 neutron. Okay, and this nucleus is what is alpha particle, and it is basically this He2 positive. Okay, 2 positive ion of helium. Okay, so this is alpha particle. So I can represent alpha particle like this. He2 4, okay, gives He2 4, okay, 2 positive ion, and 2 electrons are removed from here. Okay, so this is basically alpha particle. Okay, your alpha particle. Okay, now this alpha particle will how will you calculate the wavelength of this alpha particle? So it is very easy. Basically in the same formula. Which formula? Arre, that formula na, this formula, square root of 2m qv. You will put the values of m, q, h, etc. And after you put the corresponding values for alpha particle, you will get basically 0.101 divided by square root of v angstrom. Okay. First of all, you will get the value in meters, and then you will convert it into angstrom. Okay, so this is the value for a alpha particle, and all these formulas which I have told you today. Okay, you have to really mug up these formulas. Okay, so that you get success in the exam. If you don't remember all these formulas na, it will be very difficult for you to crack this UPSC exam with physics optional. Okay, you have to literally mug up these formulas. Okay, so this is the thing. Okay, so now we will move on towards our next topic. Okay, let's move on towards our next topic. Yes, so now everything is good. Okay, hopefully. So we had learned till here. Okay, and now we will solve a PYQ of UPSC physics optional 2002 PYQ. Okay, year 2002. This question was asked in the year 2002. Okay, so let's see if we can solve this problem easily or not. Okay, so such easy questions are asked in UPSC. You yourself will see now. Okay, a 200 electron volt increase in energy of an electron changes de Broglie wavelength by a factor of 2. Find the initial wavelength initial de Broglie wavelength. Okay, initial de Broglie wavelength of the electron. Okay, now look at this question very carefully. Okay, the question says that a 200 electron volt increase in energy of an electron. Okay, so initially the electron had some energy, and the change in energy was 200 electron volt. Okay, now tell me one thing. Okay, let me draw a line over here. Okay, so that we can differentiate over here. Okay. Okay, so this is the thing. Now let us see what is the demand of this question. Okay, so you know this very well that lambda means wavelength, de Broglie wavelength of an electron is given by 12.27 divided by square root of V angstrom. Okay, what is V over here? V is the accelerating, V is the accelerating potential in volts. Okay, so V is the accelerating potential in volts over here. Okay, and this is 200 electron volt increase in energy. Now we can't see energy in this formula at all. Okay, in this formula we can't see energy term. No, none of the term is energy over here. Okay, no term is energy over here. So we are all confused now. But after a close inspection, I see this thing 200 electron volt. Okay, I see this thing, and after close inspection, I come to know that 200 electron volt increase in energy it is saying. So tell me, uh, energy is given by Q into V. Okay, so energy is given by QV. Now, suppose I apply, suppose I have an electron. Okay, so I have an electron. Then if I apply 1 volt accelerating potential to an electron, if I apply 1 volt accelerating potential to an electron, what will happen? Its energy becomes, its energy becomes 1 electron volt. Okay, its energy becomes 1 electron volt. If I apply 2 volt accelerating potential to an electron, okay, if I apply 2 volt accelerating potential to an electron, okay, then its energy becomes 2 electron volt. Okay, now look at the question carefully. It is saying 200 electron volt increase in energy. So how much have we increased? 200 electron volt increase in energy. Okay, 200 electron volt increase in energy. Increase. Okay, increase. So clearly we must have increased the accelerating potential. We must have increased the accelerating potential V by how much? We must have increased it by 200 volts, right? We must have increased it by 200 volts. So we got to know that how much we have increased the value of V. How much we have increased the value of V? Look over here. How much we have increased the value of V, we got to know. Okay. So as we got to know this clearly, now tell me one thing. Lambda, the value is 12.27 angstrom. Okay. Let this be lambda 1. Okay. Initial. Okay. Initial this thing. Okay, your initial value of de Broglie wavelength. Okay, and you have to find this only. Okay, you have to find this. Okay, initial, because in the question it is given na, you have to find the initial de Broglie wavelength of the electron. So in order to find the initial, this is basically lambda 1 is your initial de Broglie wavelength. Okay, initial de Broglie wavelength. And what is your V1? Initial accelerating potential. Okay, Now it is given that 200 electron volt increase in energy. It is given that 200 electron volt increase in energy. So how much we have increased the value of V? We have increased it to V plus 200. We have increased the value by 200 volts. So V plus 200 is the final value. Okay. So the final de Broglie wavelength is lambda 2, and it will be equal to 12.27 divided by square root of V1 plus how much? V1 plus 200, right? Because the final, you have increased the energy of electron by 200 electron volt, na? You have increased the energy of electron by 200 electron volt, and 1 electron volt increase in energy requires 1 volt of accelerating potential. 1 electron volt, you see over here, 1 electron volt increase in energy requires 1 volt of accelerating potential. 2 volt of accelerating potential increases the energy by 2 electron volt. So 200 electron volt increase in energy implies 200 volt of accelerating potential. Okay, so 200 volt of accelerating potential extra over here, right? So this is the thing. Okay, you got this. Okay, it is in angstrom only. Okay, so lambda 2 is the final de Broglie wavelength. You can write over here that lambda 2 is your what? Final de Broglie wavelength. Okay, final de Broglie wavelength. Okay, okay. Now lambda 1 by lambda 2 we will take. Okay, so we will clearly get lambda 1 is equal to what we have? We have 12.27 divided by root over V, square root of V. Lambda 2 we have the final wavelength 12.27 divided by square root of V plus 200. Okay, so taking the ratio, now we will take the ratio. So lambda 1 divided by lambda 2 will come out to be, lambda 1 divided by lambda 2 will come out to be equal to square root of V plus 200 divided by V. Okay, you have basically divided these two things. Okay, so if you divide these two things, what you will get? 12.27 divided by square root of V divided by 12.27 again. Okay, divided by square root of V plus 200, right? Then this and this will cancel out. Okay, this will go over here, so you will get this thing. Okay, now you got this thing. Now tell me the final de Broglie wavelength. You only tell me what is given over here. Okay, increase 200 electron volt increase in energy uh, changes the de Broglie wavelength by a factor of 2. Okay, changes, it is not even given that it is increased or decreased. Okay, so you have to apply your common sense now. Okay, you have to apply your common sense now. You only tell me, if I will apply more potential, if I will increase the potential, so lambda 2 will decrease. So by a factor of 2 it has changed. So lambda 2 is clearly your smaller than lambda 1. Okay, why lambda 2 is smaller than lambda 1? Look at this formula. Look at this formula. Look at this formula. Here the denominator is bigger. Here the denominator is smaller. So naturally, your lambda 1 will be greater than lambda 2 by common sense. Okay. So it is given that the de Broglie wavelength is changed by a factor of 2. By a factor of 2 it is saying. Okay, so by a factor of 2 if it is changing, then you only tell me uh, it will be half or 2. You have two options, right? Half or 2 changes by a factor of 2. So you have two options, either half or 2. So which is possible? Lambda 1 is greater than lambda 2. So clearly lambda 1 means numerator is greater. So this possibility of 1 by 2 is eliminated, right? So you will get lambda 1 by lambda 2 equal to 2, right? So this expression will come out to be equal to 2, right? Okay. So square root of V plus 200 divided by V has come out to be equal to what? Has come out to be equal to 2. Okay. Now you take the square on both the sides. You take squares on both the sides. So you took the square on both the sides. So this come out to be equal to 4. Then you just did this thing. Okay. Simple mathematics. Okay. Then you will get 3v equal to 200. Okay. Then you will get v equal to 200 divided by 3, right? So this is the value of it is in volt. Okay, it is in volt. Okay. Now the initial, you got the value of v, right? Okay, you got the value of v. So you got the value of v like this. Now you will put it in the initial formula. Okay, you got the value of v1 or v are the same thing. Okay, v1 or v. Okay, both are same thing. Basically, if you not use one subscript also, it is going to mean the same thing, because you have directly instead of writing v2 over here, you have directly written v1 plus 200. So no need to write the subscript 1 or 2. Okay, so put the value of this 200 by 3, put the value over here. Okay, so putting the value 200 by 3 over there, what we will get? We will get simply lambda is equal to what? 12.27 divided by square root of v. But v equal to how much we got? 200 by 3 we got, right? So put this value over here. Okay, so as you will put this value over here, so clearly you will get 200 over 3. Okay, so it will become 12.27 root 3 divided by root 200. Okay, angstrom. Then you will use the calculator. Okay, then simply after this step, use calculator in your exam. Okay, use calculator and find the value. Okay, so you will get the final result in angstrom. Whatever will be the result, you will have to write it. Okay, so this was the initial wavelength of the initial de Broglie wavelength of the electron. Okay, so this was the initial de Broglie wavelength of the electron, and this was the question which had been asked in the year which year? It had been asked in the year 2002. Okay, so such a simple question was asked in the year 2002. Okay. Okay. Now we will move on towards our next topic. Okay. Now we will move on towards our next topic. Before that, I would like to give you one more question which had been asked in the year 2007. Okay. 2007, year 2007. Find the de Broglie wavelength for a thermal neutron at T equal to 300 Kelvin. Okay, so this is the question of the year 2007. Okay, and in the year coincidentally in the year 2006, same question was asked, exactly same question. But T was equal to 27 degree Celsius. Now you only tell me T equal to 300 Kelvin and T equal to 27 degree Celsius. Is there any difference? No difference at all. Okay. So there was no difference in the question in 2007 and 2006. Coincidentally, the question was repeated. So aren't science optional students at benefit? Obviously, science optional students are at benefit as compared to humanities optional students, because in humanities optional it is rare that a question is repeated exactly the same way. Okay, So here in the science optional like physics, chemistry and maths, the question can be repeated in the same with the same language with just a little bit of change. Okay, so this is the thing. So the de Broglie wavelength for a thermal neutron at 300 Kelvin you have to find. Now let's solve this question. Okay, solution of this question. Okay, you know this very well that lambda equal to h by, okay, square root of what is the value, square root of 2 mkt, right? This is the value, right? And what is m over here? H is Planck's constant. It has no doubt. Okay, Planck's constant. H is Planck's constant. Okay, what is the what does m stand for? M stands for the mass of thermal neutron. Okay, M stands for mass of thermal neutron. What does K stand for? K stands for your Boltzmann constant. Okay, K stands for your Boltzmann. Okay, and T, what is this T? It is basically temperature. Okay, you got it. Put these values over here. Okay, so when you will put these values over here, the mass of thermal neutron, Planck's constant, Boltzmann constant, and temperature. Temperature is given as 300 Kelvin. Okay, when you will put over here, you will get the desired wavelength. Okay, okay, then you will get the wavelength in meter. Okay, when you will substitute these values, Boltzmann constant has a value, say 1.38. Okay, 1.38 into 10 to the power minus 2 joule per Kelvin. Okay, this is the value of Boltzmann constant, right? So you will put these values. Mass of a neutron, I don't remember exactly. Okay, so mass of a neutron, I think mass of a neutron is equal to 1.67 into 10 to the power minus 27 kg. Okay, if I am not wrong. Okay, this is the mass of a neutron. And Planck's constant, you all know, 6.63 into 10 to the power minus 34, right? So all these values when you will put over here, you will get the de Broglie wavelength for a thermal neutron. Okay, find the de Broglie wavelength for a thermal neutron. So you will get this. Okay, but what if not a thermal neutron? If it is asked for neutrons, say. Okay, so in 2004, the question was like this. Okay, calculate the de Broglie wavelength for neutrons at T equal to 20 degrees Celsius. Okay, this was the question. So de Broglie wavelength for neutrons was the question. Now you know this very well. Do not get confused. Or okay, this formula is for thermal neutrons. Okay, the formula which has been written over here, this formula is for thermal neutrons only. Okay, this formula is for thermal neutrons. So this formula is for thermal only. Okay, thermal only. I will write over here only thermal. Okay, but over here the case is not of, I will write note over here. This is a case of normal neutrons. Okay, not thermal neutrons, and so the formula will be different. Okay, the formula for de Broglie wavelength for both of them would be different, and the formula which you will apply over here is like this. Okay, h upon square root of 3 mkt. Okay, like this. Okay, so this is the formula for thermal neutrons. It's not thermal neutron, normal neutrons. Okay, formula for normal neutrons. For normal neutrons, this is the formula. Okay, so you will apply this formula. What are the values you have to put? Okay, simply convert this degree Celsius into Kelvin. So when you will convert this degree Celsius into Kelvin, you will get 293 Kelvin. Okay, then you will put this two. You add simply 273, right? In order to calculate the value in Kelvin, you what do? You add 273, right? So you will add 273 over here, and after adding 273, you will get the value in Kelvin. The Kelvin value will be 293 Kelvin, and after that you will put the Kelvin value over here. Okay, the Boltzmann constant value over here. Okay, all in SI units. All in SI units you will put. M value you already know. Okay, M value is 1.67 into 10 to the power minus 27 kg. Okay, so what is the value of M? M value is 1.67 into 10 to the power minus 27 kg. Okay, so put these values over here. You will get the de Broglie wavelength for neutrons at 20 degrees Celsius. Okay, so the formula for thermal neutrons is different and normal neutrons is different. Okay, for normal neutrons, the formula for normal neutron, what is it? This is the formula for normal neutrons. Okay, this is the formula for normal neutrons, right? And what is the formula for thermal neutrons? For thermal neutrons, the formula of de Broglie wavelength is like this. Okay, this is the formula for basically thermal neutrons. What are thermal neutrons? So my answer is we will study it in paper 1 course, which will come soon. If I discuss it over here, then we will digress from the main. Got it? So thermal neutrons we are going to do in paper 1. Okay, so this is the thing which you have to remember. Okay, so there are similarly many questions. Okay, in 2011 also one question was asked. Okay, let me write that question also. Okay, so in 2011 it was asked In 2011, what was the question that was asked? Calculate the de Broglie wavelength. Calculate the de Broglie wavelength. 2011 question for an electron. Okay. Given that V equal to 200 volt. Okay. So de Broglie wavelength of an electron given that V equal to 200 volt. Direct question. Okay. So solution is that lambda is equal to 12.27 divided by root over V angstrom. Okay. You have to direct keep by heart this formula. Okay. Directly remember this formula for your exam. Okay. So put this value of 200 over here. Okay. Put this value of 200 over here. Then you will get whatever the value you want. You will get. Okay. So it will be something. Okay. So it will be 1.227. Okay. Divided by root 2. Okay. So you will get like that. So you will basically then you will put root 2 equal to 1.414, and using the scientific calculator you will calculate the de Broglie wavelength of electron. Okay, so so easy questions are asked. Okay, these are really very easy questions. Okay, so okay, so now we will move on towards our next topic. Such easy questions are asked. Okay, so I don't think there is any need to discuss these questions any further. Now we will move on towards our next topic. Okay. So hopefully now everything is good. Okay. So let's move on towards our next topic. That is de Broglie wavelength of a charged particle. Okay. It is basically de Broglie wavelength de Broglie wavelength of a charged particle. De Broglie wavelength of a charged particle in relativistic relativistic motion. Okay. So a charged particle in relativistic motion, how we will calculate the de Broglie wavelength of it? Okay. Naturally, the formula is going to be different from classical. Okay. Formula is going to be different from classical. Okay. So this is the thing. Okay. Now, based on this concept, only single time question has been asked. That is the year 2005. Okay. Year 2005, the question was asked, and only one time it has been asked till now. Okay. So V equal to, let V equal to accelerating potential. Accelerating potential. Okay. M naught equal to rest mass of the particle. Okay. Q equal to charge of the particle. Okay. clearly, okay, in case of relativistic motion, what is the difference between relativistic and non-relativistic? Okay, if the difference is that if we apply very small accelerating potential to an electron, then if we apply very small accelerating potential to an electron, then the motion is going to be non-relativistic. Okay, but if a huge accelerating potential is applied, then the electrons velocity and mass will show relativistic variation. Not electrons velocity, mass will show relativistic variation, and you should write mass will show relativistic variation and electrons velocity will write over here. Okay, electrons velocity will not be negligible as compared to the speed of light in. Okay, so electrons velocity will not be negligible as compared to the speed of light in vacuum. So mass will also show relativistic variation. Okay, so classical formula, all this implies. Okay, what does this imply? All of this simply imply that the classical formula will fail. Classical formula fails. Got it? So the classical formula fails. So what we were writing? We were writing this. Okay, clearly in case of relativistic motion, v approaching c. Okay, this formula implies that the velocity is approaching velocity of light, right? So clearly ek equal to kinetic energy, okay, will not be equal to, okay, half mv square, okay, as classical formula doesn't apply to relativistic world. Okay, so half mv square, this formula fails. So clearly this will not be equal to p square by 2m, right? This will not be equal to p square by 2m. Okay. Why? Because m will vary now. Because m will become a relativistic variant. It is a relativistic variant, right? So clearly these formulas can't be applied now. Okay. But since electric charge is a relativistic, now look at this. Mass is a relativistic variant, but charge is not a relativistic variant. Now let us understand this. When you accelerate a particle with velocities approaching c, if you accelerate a particle with velocities approaching c, means comparable to c, okay, comparable to c, what happens is that when you accelerate a particle with to velocities comparable to c, clearly you can see one thing, that the mass will vary according to the formula. Mass will vary according to this formula, okay, square root of 1 minus v square by c square. If you accelerate it with a very high potential, okay, very high potential, if you accelerate it with a very high potential, then clearly v will be comparable to c, and as v will be comparable to c, so v by c will not approach, will not approach 0. As it will not approach 0, so this quantity cannot be ignored. Okay, this is the relativistic variation of mass, right? This is the relativistic variation of mass with velocity. So as v by c will not approach 0, so in this formula, in the denominator we have 1 minus v square by c square, right? So v by c will not approach 0. So 1 minus v square by c square cannot be written as root 1 simply. Okay, it cannot be written like that. Okay, so 1 minus v square by c square will remain as it is, as v is comparable to c, v is comparable to c. Okay, so this tends to 1. Okay, not only 1, but it is not very much negligible as compared to this one. Okay, it is not negligible as compared to this one. Oh. Okay, so this ratio is not negligible as compared to this one. Okay, so as it is not negligible as compared to this one, so clearly you will have to you cannot use this formula. Okay, which formula? Half mv square formula, because this is clearly a classical formula, or else kinetic energy equal to momentum square divided by 2m. This formula also you cannot use, because it is also a classical formula. Okay, so we know this very well, that mass is a relativistic variant, but charge is not a relativistic variant, right? Charge does not, if you accelerate, see, if you accelerate now, if you accelerate with a very high potential, then the charge in coulombs, okay, charge in coulombs, it does not change. Okay, charge does not change. Charge does not have such a formula. Okay, charge does not have any such formula. Okay, charge does not have any such formula of relativistic variation. Charge q remains q always. Okay, even after accelerating and even after acquiring velocity, the charge q remains q only, right? So that's why I am writing this statement over here, that as mass is a relativistic variant, but charge is not a relativistic variant. Okay, so So charge is not a relativistic variant. So clearly I can write the kinetic energy formula in terms of accelerating potential and charge. So I am writing kinetic energy formula in terms of charge. Okay. Kinetic energy formula in terms of charge. Okay. So Ek equal to Qv. Okay. Doesn't matter. Okay. Let me write in another slide. Ek equal to Qv. Okay. Doesn't matter whether the motion is relativistic or not. This formula will always hold. Okay, so this formula will always hold good. Okay, so this formula will always hold good because why it will always hold good? Because Q is invariant of velocity. Okay, Q is invariant of velocity acquired by the particle. So that's why Q will remain Q always. So you can use this formula. Okay, so doesn't vary. Okay, so Ek equal to kinetic energy equal to charge of the particle multiplied by accelerating potential. You can use this formula. Okay, now we know this very well that total energy of a particle is given by. Okay, our kinetic energy was equal to this. Okay, Qv. Okay, total energy of a particle is given by what? Total energy of a particle is given by, now total energy of the particle, total energy of the particle, total energy of the particle E is equal to kinetic energy, okay, plus rest mass energy. Kinetic energy plus rest mass energy. So you will put kinetic energy equal to Qv. Okay, from here you will put over here. Okay, so yeah, I have deliberately denoted it by Ek. I have deliberately denoted it by Ek so that I can denote kinetic energy. Okay, because I am going to show total energy by E, so that's why I have denoted the kinetic energy by Ek. Okay, because I was showing the total energy by E, so that's why I am showing the kinetic energy by Ek. Okay, so Qv plus rest mass energy. What is rest mass energy? M naught c square, right? Now we can clearly from here we know this very well from Einstein's formula. Now we have two formulas. Okay, one formula is this, E equal to, okay, Qv, and rest mass energy is m naught c square. Okay, rest mass energy is m naught c square. Okay, you know this very well, right? Rest mass energy, you know this very well, na? You know this or not? Rest mass energy is m naught c square. Okay, E equal to mc square formula. Okay, Einstein's famous formula, E equal to mc square. So rest mass energy is clearly rest mass multiplied by velocity square, velocity of light square. Okay, so this is the rest mass energy. Okay, remember this formula if you don't know. Okay, so equal to Qv plus m naught c square. Now we know this very well. Now we know this, that Einstein has given another formula also, which relates energy and momentum. Okay, relativistic formula relating This is basically what? Relativistic formula relating total energy and momentum of a particle. Okay. So relativistic formula relating total energy and momentum of a particle is this. Okay. You know this very well. Now from here you can clearly write p square c square, okay, will come out to be equal to e square minus m naught square c to the power 4. Okay. Now e, the value of e, you know, qv plus what? M naught c square. So you will put this value of e in this formula. Okay. So as soon as you put the value of e in this formula, so you will get qv plus m naught c square whole square, okay, minus m naught square c to the power 4, right? Then you will take the square, okay. So as you will take the square, qv square v square m naught square c to the power 4 plus 2qv m naught c square minus m naught square c to the power 4, okay. This you will get. Then this and this will cancel out eventually, okay. And after those cancel out, you are left with q square v square plus 2qv m naught c square, okay. You are left with this, okay. So what you got finally? Finally you got p square c square equal to q square v square plus 2qv m naught c square, okay. You got this. Now you will divide both the side by c square, okay. Both the side by c square you will divide, okay. So both the side by c square if I divide, then I will clearly get, okay, this thing, okay. Okay, so both the side I have divided by c square, okay. So this is the thing which I got. Then I will put this common, okay. What thing I will put out common? I will put out common, okay. Let me show you. I will put this thing common out of here, okay. This thing, uh, uh, just a second, okay. This thing I will put common, okay. I will put out common this thing, okay. So putting out this thing common, so what you get? Just put it out common. 2 m naught qv common, okay. So as it is common now, so it will come out, this term will become 1, okay. So it become 1. This will become q square v square divided by c square multiplied by 2 m naught q v, okay. You got this. Now 1 q will cancel out from here, okay. You will get q and you will get 1 v, that is cancel out from here, like you will get v, right? So the final thing which you will get is that you will get p square will be equal to what? Your p square will be equal to 2 m naught qv, okay, 1 plus qv divided by 2 m naught c square, okay. Okay, this is the thing which you got, okay. Now you will take the square root on both the side, okay. So you took the square root on both the side. So after taking the square root on both the side, you clearly got this thing, okay. Power half, okay. Power half, okay. Now we know this very well that lambda equal to h by p. You got the value of p, right? You got the value of p. Now lambda equal to h upon p. Okay, so you know this, that you got p equal to what? P equal to this you got, right? 2 m naught qv 1 plus qv divided by 2 m naught c square. Okay, whole to the power half you got. So put this value simply here. Okay, so you will get h divided by 2 m naught qv 1 plus qv divided by 2 m naught c square. Okay, power half. You got this. Okay, now for an electron, if you put the values, okay, for an electron, simply for an electron put the corresponding values. For electron, in this formula I am saying, okay, let me take this. Okay, this formula I am saying, okay, this formula I will basically put the corresponding values for electron. Okay, so putting the corresponding values for electron. Okay, for electron I will put the corresponding values. So what I will get is lambda equal to, I will get 12.27 divided by v1 plus ev. Okay, q equal to e, right? Q is equal to e for an electron. Okay, and which it is equal to 1.6 into 10 to the power minus 19 coulomb, right? So you will put this. Okay, so 2 m naught c square, right, power half angstrom. Got it? So this is the thing. Now we will solve a 2005 year question was based on this. Okay, one of the question from the year 2005 was based on this formula. Based on this formula, a question was asked in the year 2005, and we are going to solve that question now. Okay, so let's see that question. Yes, so hopefully everything is good now. Okay, so yes, so we are going to see 2005 year question based on the formula. We had derived this formula, right? Which formula? We had derived this formula for de Broglie wavelength. The formula says that h divided by, okay, 2 m naught q v, okay, into 1 plus q v divided by 2 m naught c square, okay, power half. Okay, this is the formula for relativistic. Okay, now I will write one explanation over here. Okay, before solving the 2005 year question, I will write one explanation over here. Okay, if qv, okay, if qv is much smaller than 2 m naught c square, okay, over here, if in this formula you look at this term which I am highlighting with the laser. Okay, if you look at this term, then you will clearly see this thing, that if qv is smaller than 2 m naught c square, then this term can be clearly neglected as compared to 1. Okay, if this is the case, then this term is going to be much smaller as compared to 1. Okay, and as it will be much smaller as compared to 1, it can be neglected as compared to 1. Okay, so then the motion is clearly non-relativistic. Okay, this is the condition. Then motion is non-relativistic. Okay, if this is the case, and in that case the formula becomes your old formula. Okay, the formula becomes, in this case, what does the formula become? Then the formula becomes, we get the old formula. Okay, de Broglie wavelength old formula we get. This was our old formula, right? Square root of 2 m q v. Okay, so m is actually, you can say, it is a basically classical formula. Okay, so classical formula we get. Okay, we got the classical formula when qv was much smaller than 2 m naught c square. Okay, qv was much smaller than 2 m naught c square, so this term was neglected, and we get the old formula. Now as this is the old formula, there is no need to write the notation m naught and m. Okay, no need to write, no need to write m naught notation as rest mass and moving mass are the same in classical formula. Okay, so there is no need to put the notation m naught over here, because the rest mass and the moving mass are going to be the same as it is a classical formula. Okay, so in the classical world, the moving mass and the rest mass both are same. So if here it was relativistic formula, that's why I had to put the notation m naught in order to denote the rest mass separately. Okay, in order to denote the rest mass separately, I had to use the notation m naught over here. But in this case, the rest mass and the moving mass are going to be the same. So that's why no m naught notation is required in this formula. Okay, so that's why I have written it over here. Okay, now if qv is comparable to 2 m naught c square. Okay, the other case is if qv is comparable. Okay, oh, let me erase this. Okay, if qv is comparable. Okay, if qv is comparable to 2 m naught c square. Okay, then motion is relativistic. Then motion is relativistic. And which formula will be used in that case? Clearly your formula, this formula will be used again. Okay, so the formula on the previous slide I am writing. Okay, formula on previous slide. What is the formula on previous slide? This formula. Okay, this formula. Okay, because qv has become comparable to 2 m naught c square. Okay, qv has become, now qv has become comparable to 2 m naught c square. So this term can't be neglected as compared to 1. Okay, this term can't be neglected as compared to 1. So your relativistic formula will hold good. Then non-relativistic formula you can't use. Okay, so based on this formula, a 2005 year question was asked. So what is the approach? Okay, what is the approach to solve the numerical? Okay, approach, your approach should be very clear, that your approach should be like this. Approach to solve the problem. What should be your approach to solve the problem? First of all, find, first of all, find the value of QV and 2 m naught c square. Okay, first of all find these values. Okay, if QV is comparable, okay, to 2 m naught c square, then use the relativistic formula. Okay, and if it is negligible as compared to 2 m naught c square, then use the classical formula. Okay, so on the next slide I am discussing the 2005 year question. Okay, 2005 year PYQ of UPSC CSE physics optional. Okay, so let's write the formula, the problem. Calculate, okay, calculate the de Broglie, calculate the de Broglie wavelength for an electron given that E is equal to 1 million electron volt. Okay, so in this case you have to calculate the de Broglie wavelength of the electron. The energy is given as 1 million electron volt, or we can say 10 to the power 6 electron volt is the thing which 1 million electron volt means 10 to the power 6 electron volt, right? So so much is the energy of the electron. So you have to calculate the de Broglie wavelength. Okay, now I have already told you this thing that 1 electron volt means 1 volt of for an electron. Over here we are talking about electron, right? Over here we are talking about what? We are talking about electron over here. Okay, so clearly from this statement, if the energy of the electron is 1 million electron volt, then I must have applied 10 to the power 6 volts of potential. Okay, 10 to the power 6 volts of potential should have been applied. Okay, I had told you in the initial part of this lecture. Okay, so 10 to the power 6 volts of potential must have been applied in order to get 10 to the power 6 electron volt energy. Okay, 10 to the power 6 volts of potential must have been applied in order to get 10 to the power 6 electron volt of energy, right? So that's why 1 electron volt stands for 1 volt of accelerating potential for an electron. Okay, only for electron, not for proton and neutron. Okay, not for proton and neutron. Note over here. Okay, above concept is applicable only to electron. Okay, so the above concept that 1 electron volt energy means 1 volt of accelerating potential must have been applied. 2 electron volt 2 electron volt energy means 2 volt of accelerating potential must have been applied to the electron. 3 electron volt energy means 3 volt of accelerating potential must have been applied to the electron. 4 electron volt means 4 volt of accelerating potential must have been applied to the electron. Okay, so things like that. So I mean to say that 10 to the power 6 electron volt of energy of the electron implies that 10 to the power 6 volts of potential must have been applied to the electron. Okay, so 10 to the power 6 volts of potential must have been applied to the electron. So the value of V becomes 10 to the power 6 volts. Okay, this becomes the value of V. Okay, now you will calculate the value of QV and you will calculate the value of 2 m naught c square. Okay, so in order to compare, okay, in order to see whether I will apply this formula or this, okay, you have to see, right? You have to see whether you can apply this formula, which is the non-relativistic formula, that is classical one, or whether you can apply this formula. Okay, so in order to see that, I will calculate the QV value and 2 m naught c square value. Okay, so I will first of all calculate the QV value. Okay, so QV value comes out to be 1.6 into 10 to the power minus 19 multiplied by 10 to the power 6. Okay, so it is coming out to be 1.6 into 10 to the power how much? Minus 13. Okay, this much is the QV value which is coming out. Okay, and 2 m naught c square value, what does it come out to be? 2 multiplied by 9.1 into 10 to the power minus 31. Okay, mass rest mass of an electron, rest mass of an electron is 9.1 into 10 to the power minus 31 kg, and so that's why I am putting the values over here. And after you put the values over here, what do you get? You will get something. Okay, you will get something like this: 2 into 1 9.1 into 9, right, multiplied by 10 to the power minus 31 plus 16, how much will it be? 15. Okay, 10 to the power minus 15, I think. Okay, it will be like that. Okay, then you will calculate clearly this term. So this term comes out to be how much? 9.1 multiplied by 18. So this term comes out to be 8 ones are 8, 8 nines, 9 8 is 72, and this is 91. So it will be 3 9 and 7. It will be 16. Okay, so it is coming out to be 16. How much it is? It is coming out to be equal to 16.38. Okay, 16.38 into 10 to the power minus 15, it is coming out like that. Okay, so then you will just do this thing, that it will be then 1.6 uh, into 1.638 into 10 to the power. I think there is some okay, there is some mistake over here, I think. Okay, there should be 9.1, 8 to 8 to the 16. So 31 and 16, how much do they make? Okay, 16 to the 32. So it will be like that. Okay, so 1.6 into 10 to the power minus 14, right? So clearly this can't be neglected. Okay, you can clearly see this, that this ratio can't be neglected. Okay, clearly you can see this thing. Okay, when you will calculate the value of QV and you will calculate the value of 2 m naught c square, these values clearly can't be neglected. Okay, you yourself do this, you will eventually understand it. Okay, so no, sorry, it is not 16.38. It will be 163.8 over here, and then it will. So basically, the value of 2 m naught c square is also coming out to be the same. Okay, 2 m naught c square value, if you calculate, it is coming out to be the same. Okay, it is coming out same only. Okay, so clearly, so you will write clearly QV. Okay, is approximately equal to 2 m naught c square, right? So the formula, so which formula can't be applied? So the formula lambda equal to h divided by square root of 2 m q v cannot be applied as the motion is relativistic, right? So this formula clearly can't be applied. Okay, so which formula will you apply then? You will clearly use this formula. Okay, lambda equal to h divided by, okay, 2 m naught qv, okay, 1 plus qv, okay, 2 m naught c square, okay, power half. You will apply this formula. Okay, so now after putting these values over here, you got to know that qv is coming out approximately equal to 2 m naught c square, right? So what are you getting over here? You are getting that h divided by 1 plus 1, okay, 1 plus 1, okay, so it will become 2, so it is coming out to be 4 m naught qv to the power half, it is coming. Okay, so after that you will put the values for electron. Okay, what are the values for electron? You clearly over here the value of v is 10 to the power 6 volts, right? Value of q you already know for an electron, 1.6 into 10 to the power minus 19 coulomb, right? And the value of m naught for an electron is equal to 9.1 into 10 to the power minus 31 kg. Okay, so 9.1 into 10 to the power minus 31 kg. Okay, all these values when you will put over here, you will get the de Broglie wavelength of the electron. And this 2005 question can be solved in this manner. Okay, so in the year 2005, what they have done? They have basically twisted the question. Okay, up to in the year 2005, what mistake did the UPSC aspirants do? Okay, uh, they performed they performed in the year 2005. I am telling at that time what the students mistakes they did. They performed the mistake of using classical formula. Okay, and up to year 2004, coincidentally, all problems were based on classical formula only. All problems up to here were based on classical formula. So eventually all this led to the attempt being wasted. Attempt was wasted. Okay, so beware. Okay, wasted. So beware of such things. Okay, sometimes the UPSC examiner wants you to be well acquainted with the all the type of concepts. Okay, sometimes they want you to be well acquainted with all types of concepts. So this is the thing. Okay, so in this manner you could have solved the 2005 year PYQ of UPSC CSE physics optional. Now let's move on towards our next topic. Okay, yes, so let's move on towards our next topic. Okay, so the topic is regarding phase velocity. Okay, the topic says phase velocity, and in this course there is going to be 100% coverage. Okay, so don't worry, there is going to be 100% coverage. Okay, of the syllabus. Not even a single thing will be left. Okay, not even a single thing will be left. So be calm and patient. Okay, now let's move on towards our next topic, which is phase velocity. Okay, phase velocity, which is denoted by Vp. Okay. Ultimately, all these things are going to come in paper 1. Okay. All the things which I will be discussing in the next 20 minutes. Okay, let me write over here. All the things which I will be discussing in the next 20 minutes are already being recorded for paper 1. Okay, so all these things are there in paper 1, your paper 1 syllabus. So don't worry that I didn't understand the meaning of phase velocity and all. Don't worry about that. All these things are already being recorded for paper 1 purpose. Okay, so so if even if in case you don't understand anything from next 20 minutes, just accept the formulas and move ahead for the time being, as these things are a part of paper 1 syllabus. Okay, so just accept the things which I am going to tell you in the next 20 minutes. Okay, now regarding phase velocity, we are going to write something. Okay, we are going to write something regarding phase velocity. Okay, so your phase velocity Vp. Okay, so in the next 20 minutes some of the facts are going to be discussed which are actually from paper 1. Okay, but in order to understand quantum mechanics, we are going to require these things. Okay, so if someone does not have the knowledge of paper 1, even then he should be able to take the advantage of this paper 2 course. So that's why I am writing some of the facts here. Okay, phase velocity. Okay, phase velocity. Phase velocity symbol is Vp. Okay, Vp is equal to your omega upon k. Okay, Vp is equal to your what? Omega upon k. Okay, now omega is equal to your 2 pi mu, right? Just accept them as it is. Okay, just accept them as it is. They are going to come in paper 1. All these formulas will be derived in paper 1. Okay, all of these formulas are going to be derived in paper 1, so don't worry if you don't understand them. Don't panic. Okay, so mu lambda. Okay, let this be equation number 1. Okay, now Vp is equal to h cut omega divided by h cut k, right, which is equal to E upon P. Okay, which is equal to mc square divided by mv. Okay, which is equal to c square over v. Okay, so you got this thing, that this formula also you will have to remember, Vp is equal to c square upon V. Okay, this formula is important, and this is equation number 2. Okay, so that is, we know this very well, that Vp Vp into V is equal to your c square. Okay, so this can be written this way also. Okay, that phase velocity into particle velocity is equal to c square. Phase velocity into particle velocity is equal to c square. Now there are some remarks over here. Okay, so you come to know over here that this product Vp into V, this product is equal to c square. Okay, now your particle velocity will be always smaller than c, because I have already told you in the special relativity marathon session that no material particle, okay, let me write over here, no material particle or signal can travel at a speed greater than the speed of light c in free space. Okay, so no material particle or signal can travel at a speed greater than the speed of light c in free space. So according to this principle of this is the postulate of relativity. Okay, this is one of the postulates, one of the postulates one of the postulates of special relativity. Okay, now you only tell me that over here particle velocity, this is particle velocity, right? So particle velocity is smaller than c always, according to this concept. Okay, according to this concept, your v will be always smaller than c. Okay, so naturally your phase velocity as the product is c square. Okay, so let me write over here. Okay, vp into into v, vp into v is equal to c square, right? Vp into v is equal to c square, right? Now you only tell me that if V is always smaller than C, then obviously Vp will be always greater than C, right? Common sense, na? See, I am writing over here 3 square. Okay, suppose. Okay. Suppose I write over here 3 square. Okay. So if I write 3 into 3, then it's okay. Okay. Suppose this is Vp and this is V, suppose, and this is suppose C square. Okay. Now I want to decrease the value of V. Okay, so suppose the situation is that V is always smaller than 3. Suppose the situation arises that V is always smaller than C. Okay, so in this case V will be smaller than 3. So obviously if you put 2 in this equation, okay, so clearly you can see this thing, that Vp comes out to be equal to what? 9 by 2 means 4.5. Okay, so Vp is greater than 3 then. Okay, Vp is greater than 3 because the situation is that V is smaller than 3. So Vp had, if the V value is reduced to 2, then Vp's value increases to 4.5. Okay, so that the product remains c square only, right? So this is the case why the phase velocity will be always greater than c. Only thing is that we have c in the place of 3, we have some other figures. Okay, nothing is the difference. So if V is smaller than C, then obviously Vp will be greater than C, so that the product remains the C square. Okay, so if the product remains C square, then obviously if you decrease this, then you must increase this. Okay, so that the product remains constant. Okay, so this is a situation that V is always smaller than C, and we know this very well, that C square equal to C into C. So if I compare these two, Vp into V, and if V is smaller than C, okay, this is smaller than C, okay, less than C, so obviously I will have to make this more than C, so that the here C into C compensates for C greater than C multiplied by C smaller than C. Okay, so that's why Vp will be always greater than C. Okay, so Vp will be greater than C. But some of the students get confused over here. They see that the phase velocity is coming out to be greater than the velocity of light c, so they think that it is violation of special relativity. No, it is not a violation of special relativity. Let me write over here. Okay, Vp greater than c, no violation. Okay, there is no violation of special relativity. Okay, SR stands for special relativity. Okay, as the wave does not carry energy or information at velocity Vp, but it takes place at velocity Vg, okay, which is group velocity. Okay, and Vg is smaller than c always, and Vg is smaller than c always. So understand the statement. Okay, as Vp is greater than C, some people think that it is violation of special relativity, but it is not a violation of special relativity, because the wave does not travel at this speed. The matter wave which we get na, matter wave does not travel at Vp speed. Okay, matter wave travels at Vg speed. Okay, the speed of matter wave is Vg. Okay, so energy or information of the matter wave does never travels with the velocity phase velocity. Okay, it always travels with a velocity called as group velocity, and this group velocity is always smaller than c. Okay, so that's why Vp will be greater than C. Okay, so that's why there is no violation of the special relativity, because what does special relativity tell? That it says that no material, particle or signal can travel at a speed greater than the speed of light c. Okay, it tells like that. So no material, particle or signal can travel at a velocity greater than c. But the violation of special relativity would have occurred if Vp velocity would have been the velocity at which the particle is traveling. But is this the case? No. No particle is traveling with the velocity Vp. Okay, matter wave particle does not travel with velocity Vp. Matter wave particle travels with velocity Vg, not Vp. Okay, so it is not a violation of special relativity that the speed has become greater than c. Okay, there is no violation of special relativity, because the speed is still smaller than c, because it is traveling with a velocity called as group velocity instead of a velocity called as phase velocity. Okay, so it is traveling with group velocity, so there is no violation of special relativity, as the group velocity is always going to be less than c. Okay, as the group velocity is always going to be less than c. Okay, so even if Vp is greater than c, if someone fools you in the interview, UPSC interview, if someone wants to fool you, then they may ask this question, but you will have to be very alert. Okay, Vp greater than c does not imply that the special relativity has been violated. it only means that the phase velocity is greater than c, but that particle does not at all travel with the velocity phase velocity. Okay, it only travels with the velocity group velocity, so there is no violation of special relativity even though vp is greater than c. Okay, so no violation of special relativity as the wave does not carry energy or information at velocity vp. Okay, wave does not carry energy or information at velocity vp, but it takes place at velocity vg instead of vp. It takes place with a velocity vg, which is called as group velocity. Okay, and vg is always smaller than c. Okay, so there is no violation of special relativity. This thing you will have to remember. Okay, okay. Now we will move on towards the next concept, which is group velocity. Okay, group velocity. All these things are going to come in paper 1. Okay, I am just using this as a passing reference so that in the paper 2 you don't feel uncomfortable in the next lectures, upcoming lectures. You don't feel uncomfortable. That's why I am basically telling you all these things over here. Okay, let this be equation number 3. Okay, so hopefully you are noting down everything. Okay, if you are just sitting idle and watching na, then I don't think there is going to be any benefit out of it. Okay, I think so, like that. Okay, h cut e by h cut, which is equal to mc square divided by, okay, h cut. Okay, e equal to mc square, so e by h cut equal to mc square by h cut. Okay, e equal to h cut omega. Okay, all these formulas you have to be on your uh, fingertips. Okay, these formulas should be there on your fingertips. H cut 1 minus v square by c square power half. Okay, so the formula for m formula would be m naught divided by 1 minus v square by c square square root. Okay, you know na how this came, because the special relativity tells that the mass variation with velocity, right? Mass variation with velocity is like this. Okay, 1 minus v square by c square power half, right? So this is the variation of mass with velocity according to special relativity of Einstein. So I have put the value of m over here because we will take the moving mass. Okay, we are going to take here moving mass because we are talking about group velocity. So group velocity is all about moving mass, and as group velocity is all about moving mass, so we are going to take over here moving mass in this formula. We are going to take over here moving mass instead of stationary mass. Okay, and so moving mass and stationary mass are related like this. Moving mass and stationary mass are related like this. So I will put a value of m like this over here, and I will get the value of omega like this. Okay, then I will just find out the value of, now I have got the value of omega, right? I have got the value of omega. How much? Omega value I got m naught c square, right, divided by h cut 1 minus v square by c square power half, right? This is the omega value which you got. Okay, so you will find eventually d omega over here. Okay, and as you will find d omega over here, you will clearly see this thing that m naught divided by h cut will be out of the differential, and your differential remains like this. Okay, so 1 minus v square by c square, okay, power half, right? Then you will do what will you do then? Okay, then clearly you will apply the formula. Okay, then let me write on the next slide. Okay, what you got? D c square, you got this, right? D c square divided by 1 minus v square by c square to the power half. Okay, 1 minus v square by c square to the power half, right? This is the thing which you got. Okay, so how to solve this differential I am telling you. Now you look at the thing carefully. Okay, d, okay, this c square is going to come out eventually because the c square is a constant, so c square has come out. Okay, now 1 minus v square by c square, in the denominator the power is half, so it will go in the numerator. Okay, and numerator it will become minus half, right? So then we will apply that formula of chain rule. Then what will happen? C square multiplied by minus half will come in the forward direction. Okay, minus half is going to come here. Okay, so minus half comes over here. Okay, minus half comes over here, and then you subtract 1 from minus half. Okay, you subtract 1 from minus half, so you will subtract 1 from minus half. Okay, 1 minus v square by c square. Okay, power minus 3 by 2, right? Then after that you will basically differentiate this thing. Okay, so when you will differentiate this thing, what will you get? You will differentiate that thing, then you will get d minus v square by c square, right? You will get this thing. Now look at this thing very carefully, that this what will this become? D minus v square by c square. What will this become? 1 upon c square is going to come out. Okay, and it will become minus 2v, right? So you will write over here, instead of this you will write what? Just erase this. Okay, and write this thing over here. Just erase this and write this thing over here, which you got in the above over here. Okay, so you will write multiplied by 1 upon c square minus 2v, right? So eventually your minus half and minus 2, these are going to cancel out. C square and c square is going to cancel out. Okay, so and dv will remain over here, right? Dv will remain over here, right? So what you got? You can see in the previous slide, you got basically this thing. Okay, that it came out to be v dv. Okay, it came out to be m naught by h cut. Okay, equal to m naught by h cut v dv divided by 1 minus v square by c square power 3 by 2, right? Okay, so you got this thing. Okay, and this let this be equation number 4. Okay, let this be equation number 4. Okay, so you got this equation. Okay, now what is the thing? Okay, again p equal to h cut k. Okay, again, okay, again p equal to h cut k. Okay, again p equal to h cut k. So k will be equal to your p by h cut, right? P will be equal to your p by h cut. So it will come out to be mb divided by h cut. Okay, so it will come out to be your what? uh, m naught v. Okay, m naught v, m naught v divided by h cut 1 minus v square by c square. Again 1 minus v square by c square to the power half. Okay, the way you found d omega, you will now find dk. Okay, so again you will use the same thing. Okay, m naught by h cut, then you will use the differentiation on this. Okay, this thing will come out of the differential. Okay, this thing will come out of the differential. M naught by h cut will come out of the differential, and only thing which will remain inside the differential is this thing. Okay, only thing which will remain inside the differential is this. Okay, so this thing will remain inside the differential. So after you simplify, you will simply get this thing dv divided by 1 minus v square by c square power 3 by 2 you will get. Okay, now tell me that dk is equal to this you got. Okay, so let this be equation number 5. Okay, now vg equal to d omega by dk. Okay, you got the value of d omega, right? You got the value of d omega. How much you got the value of d omega? This much. And how much you got the value of dk? This much. Okay, so I will write them on the next slide once again. D omega is equal to your m naught by h cut. Okay, v dv divided by 1 minus v square by c square. Okay, power 3 by 2. Okay, This is your equation number 4 accordingly. Okay, and this is your decay, which has come out to be equal to, by taking the differential on both the side, you got this thing. Okay, 1 minus v square by c square power 3 by 2. Okay, this is the equation 5 you got. Now simply do one thing, that take the ratio of these two. Okay, take the ratio of these two. What will you get? Vg is equal to your d omega by dk. Okay, so although it is not divided by, never call this divided by. Okay, d omega by dk symbol does not imply that d omega is being divided by dk. No, they are not being divided. Okay, d omega is being divided by dk. It does not imply like that. It is only a differential operator. Okay, for our convenience we are assuming that we are dividing it. Okay, see what is that. The thing is that in the UPSC exam, in the interview, the person may ask you, the interviewer may ask you that you have d omega, you have dk, right? And you have over here Vg equal to d omega by dk, right? So you have d omega and you have dk, and over here you have Vg equal to d omega by dk. So does it imply that we are dividing d omega and dk? Can we write over here? Okay, never write in the exam that dividing 4 by 5. Never write this in the exam. Your marks will be deducted, beta. Marks will be lost. Okay, why? Because d omega by dk does not mean. Okay, let me write over here. Okay, d omega by dk doesn't mean that d omega is being divided by dk. Okay, so do not write dividing equation 4 by 5. So never write this. Okay, if you got the value of d omega, if you got the value of dk, then never write that dividing 4 by 5. Okay, only thing is that you have got the value of d omega and dk. Now for our convenience we are imagining it like that. Okay, हम ऐसा imagine कर रहे हैं कि d omega और dk जो है हम यहाँ से ले रहे हैं, ठीक है ना? We are assuming like that. Okay, for our convenience we are imagining that we are dividing d omega by dk. For our convenience we have assumed that, but that is not the reality, because this is a operator. D omega by dk, this is differential operator, so it can never be considered that d omega is being divided by dk. So you can never use the sentence over here that dividing equation 4 by 5. Never use this. Marks will be lost, beta. This formula, this statement never used in the exam. That dividing equation 4 by equation 5. Marks will be lost, because these are differentials, not ordinary quantities. Okay, these are differentials, not ordinary quantities. So you cannot write that they are being divided. Okay, it is completely wrong to say that. For our convenience, we are just assuming. Okay, in the mind we are thinking. In the mind we are thinking that it is looking like, ये ऐसा दिख रहा है, डिवीजन समान दिख रहा है, ऐसा हम मन में सोच के उसको लिख रहे हैं, लेकिन वैसा है नहीं असलियत में, ठीक है ना? तो नेवर राइट दैट स्टेटमेंट. ओके, ओवर देयर. So you will get d omega by dk. After you find the ratio, just put these values over here. Okay, so as you will take the ratio, then what will happen? This thing and this thing will cancel out. This thing and this thing will cancel out. This thing and this thing will cancel out. So what will you get ultimately? D omega by dk you get equal to v ultimately. Okay, so now vg equal to v. Okay, so vg equal to d omega by dk is equal to v you got, right? Now vg equal to v equal to that implies, okay, that implies that group velocity is equal to particle velocity. Okay, so it can be asked in the exam that prove that group velocity is equal to particle velocity. Okay. So your group velocity has come out to be equal to particle velocity, and this Vg is going to be always smaller than c, because special relativity postulate. Okay. Special relativity states na that no material, particle or signal can travel at a speed greater than c. So if the particle is traveling with the velocity group velocity, then you only tell me, can the particle ever can the group velocity ever be greater than c? Never, because the special relativity says that it is equal to particle velocity na. So that's why the particle velocity, you only tell me the particle velocity is always going to be smaller than c, right? Particle velocity is always going to be smaller than c according to special relativity, and you are saying that Vg equal to v, group velocity equal to particle velocity. So this in turn implies that group velocity will be smaller than particle velocity. Okay, so Vg is your smaller than c. Okay, and this is always okay, this is always, this is a rule always, that you are for a matter wave, let me write over here. Okay, for a matter wave, for a matter wave, group velocity is always going to be less than velocity of c. Okay, so for a matter wave, group velocity is always going to be less than the velocity of light c in free space, that is वो तो है. Okay, in free space. Okay, so this is the thing you got. Now relation will between Vg and Vp again. Okay, relation between Vg and Vp, relation between Vg and Vp, that is group velocity and phase velocity. Okay, this is what group velocity, and this is what phase velocity, right? Okay, so group velocity and phase velocity have a relation, and this relation is going to be derived in paper 1. Okay, this relation is going to be derived in paper 1. Paper 1 course, this relation is going to be derived. Okay, so what is the relation? Relation is like this. Okay, Vp minus lambda dVp over d lambda. Okay, lambda dVp over d lambda. This is the relation between Vg and Vp, which you will derive in the paper 1. Okay, paper 1 it is going to come. Okay, now show that now there is an important problem. Okay, show that Vp equal to V by 2. Okay, show that Vp equal to V by 2. Show that Vp equal to V by 2 for a free particle. Okay, for a free particle in non-relativistic motion. So we have to show that phase velocity is a half of particle phase velocity is half of particle velocity. Okay, we have to prove this, that phase velocity is half of particle velocity. Okay, phase velocity is half of particle velocity. Okay, so we have to prove this now. Okay, so in order to prove this, let us consider that the proof is over here. Okay, proof is over here. Let this Vp equal to, you know this very well, that okay, let this be equation 1. And how this came? From paper 1, which I am going to discuss later. Okay, from paper 1. Okay, then you have lambda equal to h upon p, right? You have lambda equal to h upon p, so h upon mb it will be. Okay, let this be equation number 2. Okay, then according to classical formula, okay, now what will be the total energy of the particle? Okay, from here we can see one thing, that it is written free particle. Okay, what is written? Free particle has been written over here. Okay, so let me write one thing over here. What does this free particle imply? Okay, free particle simply implies, okay, free particle simply implies that the particle has zero or constant potential energy. So for any particle in this world which is free, okay, for any particle in this world which is free, it is very clear that either it has zero or it has a constant potential energy. Okay, what is a free particle? Free particle is such a particle which has either zero or constant potential energy. Okay, so it is free from all interactions. Free particles is such a particle which is free from all kinds of interaction of the world. It is completely a kind of isolated kind of particle. Okay, it is free from the interactions of the world. No force is acting on it. Okay, so such a particle is called as free particle. It is out of the force field. Okay, it is out of the force field. Okay, so the particle has zero or constant potential energy. Now I have told you one concept, even in the 11th and 12th standard, even in 11th and 12th standard, you might have learnt one concept. Okay, in the 12th, you might have learnt one concept. The concept says that potential energy is always defined in terms of relative, means potential energy is a relative term. Okay, you might have learnt in 11th and 12th that between 2 points in this universe, okay, between any 2 points in this universe, between any 2 points in this universe, only potential difference is defined. Okay, you have learned this very well in 11th and 12th, that between any 2 points in the universe, only potential difference is defined. Potential, absolute potential is never defined in this world. You have learned this thing very well. Okay, so if only potential difference is defined between 2 points, potential is not defined. So what do we do in order to define potential? Potential, how do we define potential then? We just take that the infinite point has zero potential. We consider that at infinity the potential is zero, and we calculate the potential relative to that infinity point which has zero potential, and we call that it is the potential of this point, right? So potential is always defined in terms of it is a relative term. So obviously, if a particle has constant potential energy, then I can take it zero also, right? If a particle has constant or zero potential energy, why not take it zero? Just take it zero, na? Because you see one thing, it is a relative which is defined. Okay, so let me see, if I say that the potential at this point is 3 and at this point the potential is 4. Okay, so the potential with respect to 3 is 1 over here. Okay, the potential with respect to 3 is 1 on this point 4. Okay, on this point 4 the potential with respect to 3 is 1. Okay, because 4 minus 3 equal to 1, right? But if what if I assume the potential to be here only? Okay, if I assume the potential to be here only with respect to this, I am going to get 4 minus 4 equal to 0. So it is my arbitrary assumption, na? Only potential difference is defined in this world, so it is my arbitrary assumption then that where I want to take the zero potential. Okay, so if I take the particle itself as zero potential, then obviously I can take it because it is a free particle, it is free from interaction, that's why I can take it. It is free particle, that's why I can take its potential to be equal to zero. Okay, so hopefully you got this thing. Okay, so what will you write then? You can write this thing very well, that the total energy will be given by, so let me write those two formulas over here. Okay, this is one formula number 1 and this is formula number 2 which you got. Okay, H over mv. Okay, now total energy, your total energy is equal to E is equal to half mv square. Okay, so plus 0. Why it is like that? Because total energy, this is total energy. Okay, this is kinetic energy plus potential energy. So potential energy is already 0, so only kinetic energy I have, so I will write kinetic energy only. And in this world, write this note. Okay, write this note that a free particle in this world only possesses kinetic energy, and all other kinds of energy are 0 for it. Okay, so whenever you see a free particle in this world, in this physics world, if you see any free particle na, just assume that it has only kinetic energy. This is a rule. Okay, a free particle will only have kinetic energy, no other energy it will have. A free particle will only have kinetic energy, and no other energy, no other. Okay, no other energy it will have. Okay, it will only have kinetic energy. A free particle will only have kinetic energy, no other energy. Okay, so according to that formula I have written this. Okay, according to that concept, so you got this. E equal to half mv square. Okay, E equal to your half mv square. Okay, so E equal to your half mv square. Okay, then I can write h mu equal to half mv square, right? Because E equal to h mu by Planck's formula for energy. So mu yani ki frequency. So your mu, that means frequency will be equal to 2 mv square by 2h. Okay, and let this be equation number 3. Okay, so Vp, how much will be Vp then? You know this very well, that Vp equal to mu lambda, right? And you have already found out lambda in the previous slide, that it was equal to what? H by mb. It was equal to h by mb, right? So you will put these two values over here. So what will you get? mb square by 2h multiplied by, okay, h by mv. Okay, so m and m will cancel out. Okay, v and v will give you single v. Okay, and h will cancel out, 2 will remain. Okay, so you will get v by 2 ultimately. Okay, so vp equal to v by 2. This is the proof you got. Okay, vp equal to v by 2, and this is the thing which had to be proved, and this is your pyq. This is your pyq, one of the pyq. Okay, So this is the one of the PYQ. Okay. So hopefully up to here everything is good for you. Okay. So I will end the class here. See you in the next class.